So welcome everybody. Today's webinar is on VI probes and in particular Matchbox characterization. So let me take you through an outline of what we're going through today. We're going to start off, I'm going to just do a basic run through of the RF power delivery network, right? So we'll do this in a few slides. I'll talk about 50 ohm region, the non-50 ohm region, and the Matchbox in the middle, and kind of what's going on there. So if anyone here is relatively new to RF, my goal is to give you an intuitive understanding of what's going on, throughout this network, okay? So we'll probably spend about 15 minutes on that. And I'll give a quick intro to the Octiv VI probe. That's the technology we're going to use to do the mapping today. So I'll just mention the specs and I'll show you like some pictures of it and what it can do. Then I'll do a brief explanation of what is Matchbox characterization. Why do we do it? What's the goal? What's the result of doing this? And then we'll do a live demo. So the live demo will be in 20 minutes, maybe 25 minutes time, where we'll just map out a Matchbox. We'll do this with CWRF, and then we'll do it with pulsed RF, okay? And after the live demo, we'll talk about some of the other things that a VI probe can do, okay? Yeah, so we'll get started. I'm based up in the office. I'm actually remotely connecting to the VI probes that are down on the lab. So I'm hoping the Wi-Fi doesn't let me down. We'll see how it goes. We've also made videos on a new video on the on how to do this mapping technique. So we'll also release that video afterwards for people to watch again. Just a brief introduction to Impedans. We're based in Dublin, Ireland, and we were founded in 2004. And we're 40 plus employees and a global distribution network. Mostly R&D people, mostly people with plasma physics background, but also manufacturing and logistics and administration and so on. And our focus is basically to provide advanced plasma and RF diagnostics for primarily the semiconductor industry, but also like university and research markets. So we're a provider of plasma and RF diagnostics, essentially. So let's get into the RF power delivery network. I want to go through the basics, and I really mean I'm going to start at the very basics, okay? So here's a simplified look at the RF network, okay? Very simplified. So we have a generator, we have a cable, the matchbox, another cable or transmission line, and then plasma reactor. And every single part of here, this network has an impact on every other part, okay? So the plasma impacts everything before it, but the generator impacts everything after it as well. So keep this in mind. And also remember, the cable is a part of this network, okay? The cable properties matter. You can get cables that are not very efficient. You actually have power loss in a cable per unit length. You have to consider cable lengths with respect to RF wavelength and things like that. And also, after the matchbox, you have this non-50 ohm region, which is where the transmission line physics becomes quite complicated. So let's go through this section by section and let's talk about what happens there. So firstly, there's what we call the 50 ohm region, okay? So this is the bit that's from the generator to the entrance of the matchbox, okay? So here's a typical, this is an AE generator here. And then the matchbox here is represented by tuning capacitors and an inductor. And, here's a picture of one with some tuning caps and you can see the inductor in there. And I've labeled this region 50 ohms. And you should literally think of it as, if it's working ideally, it's like a 50 ohm resistor. Okay, so it's like a resistor in line. And we require all this equipment in order to run a plasma. The plasma can also be thought of a circuit. This is not a real plasma equivalent circuit, but from the radio frequencies point of view, the plasma is actually a circuit, which is where the impedance comes from and where the harmonics come from and all this sort of thing. That's a topic for another day. So a little refresher, what does 50 ohms even mean? You've heard this word a lot, but what does it actually mean, okay? So 50 ohms refers to the impedance of the circuit. And impedance, you need to think of, it's resistance, but for AC, okay? So in AC, you have resistance. In DC, you have resistance. In AC, you have impedance. And impedance is a complex number, so it has a real and imaginary part. And real basically is DC resistance, okay? Whereas the imaginary part is essentially how the circuit reacts to the changing voltages and currents because the voltage is going up and down, the currents are going up and down, okay? So there's the DC resistance part, and then there's the reactance part, okay? And the 50 ohm region should be 50 ohms of real impedance, like the DC resistance, like a resistor, and 0 ohms imaginary. And that's written like this, like 50I plus 0J ohms, okay? And like, what does this mean quite simply? If your generator is a volt, like it outputs a voltage, okay? And based on that voltage, you're going to get a current. And very simply, the voltage will be 50 times the current. That's all this means, okay? So here's a practical example. 500 watts into 50 ohms. Your current, based on this equation here, so this is just doing P equals I squared, or is equal to 50, rearranging. So we get current is square root of power over 50, because it's 50 ohm region. So you're going to get about 3.1 amps, 3.16 amps. And then if you then calculate the voltage, it's going to be about 158 amps, 58 volts, sorry. So you get the idea. 50 ohm region just means you have this fixed relationship between the voltage and current, okay? And the generator is designed that when, 158 volts is being output, it can output the 3.16 amps. So it's designed to match with the 50 ohm region, okay? Let's go into a bit more detail about that. What do we even mean by match? What's that about? Okay. So let's talk about forward and reflected power. Okay. So the generator outputs power into 50 ohms, okay, into a cable. But at the other end of this network is a plasma, and the plasma can be any impedance, and it's an imaginary impedance, right? So it's a complex number, okay? It can be anything. So when the power reaches the end of the 50 ohm region, if there's a sharp change in impedance, power will reflect back. So what does that even mean? Like what's going on? And I think the easiest way of understanding this is thinking of it in terms of light, okay? So I want you to think of, the cable like being air and the plasma being glass, okay? And air has a refractive index of about 1. Glass has a refractive index of like 1.3, 1.5. You may remember this from earlier physics. And if you have a sharp boundary, it means only some light will go through and some will reflect. So if you have a look at this laser light, you see this is the forward power, okay? It hits an area which is a different impedance, a different refractive index. Some will be transmitted through, and some will be reflected. So what's transmitted through is called the delivered power, and what's reflected is the reflected power, okay? So I want you to imagine this every time you think of forward and reflected power. And our goal is to make this boundary not so sharp. We want to have a smooth transition between air and glass. So we want to have a smooth transition between the generator and the plasma. So here's a diagram here, which is sort of saying, right, your impedance here is 50 ohms. And then at your plasma, it's something weird, 72 plus minus 12J, whatever. But think of that as refractive index 1 and refractive index 2. And when there's a sharp change between them, you get the reflected power. Okay? So that's your intuitive way of thinking of it. So how do we solve this? To solve this with RF, we introduce what's called the matchbox. Okay? So the matchbox tries to, the way I envision it, to think of it intuitively, is the matchbox makes a smooth transition between the two impedances, okay? So the matchbox has some sort of circuit, and this kind of draws a smooth line between the 50 ohms and where you need to go. That's my way of thinking of it, okay? And if the matchbox is not doing a good job, you get reflected power. And your goal is to get reflected power to 0, okay? And you should really aim for 0. The closer to 0, you're going to have better process stability, better generator stability, less stress on the matchbox itself, these sort of things. So you really want to aim for 0. And I mean 0.000, like you want to get all the way down. Let me go into a bit more detail. If you're having plasma trouble, you can't always just stick in a diagnostic, okay? You have to be as non-invasive as possible. So one of the easiest things to do is to look in the 50 ohm region. So if you're having process stability issues, you want to check the match performance. And I think this is pretty common in fabs. Blame the RF first, okay? So you want to check, is the impedance 50 plus 0 ohms from the generator output? So you can do that with a VI probe. It can measure the impedance. What is the impedance? Is it reaching 50 or not? You can check the forward and reflected power, and these are usually, on the generator output, like the, well, I'll explain what I mean by generator output here. So where you measure these parameters is important, okay? Because you have a cable of some length. And if you're in a fab, you have a cable, you have a generator in a sub-fab, which could be 10 meters down from your actual, plasma on a different floor, okay? So you have a very, very long cable. So you have to be careful where you actually do these measurements. As a general rule, you want to make sure that the generator sees 50 ohms. So that means if you were to place an impedance measurement device here, that's where you should read 50, okay? Can argue a bit about this, but I think as a general rule, this is where it should be. And if you're checking like power delivered, like if you're checking the generator output, it doesn't really matter what's being output at the front face of the generator. What really matters is what's making it to the front face of the match, okay? So if you've developed a process at 2 kilowatts, okay, like 2 kilowatts generator output, and then you introduce a 10-meter long cable, it's not 2 kilowatts making it to the match anymore. You lose actually, for 10 meters of cable, you're going to lose about 10% of your power, even with a good cable. It's going to heat up. So what you really want to do is check what is my power delivered to the match after the cable. Because the cable can also be faulty. Like over time, cables go through heat cycles. That means they degrade, they get more resistive, their capacitance changes. They become, they do have to be replaced occasionally. So you want to measure after the cable, okay? So yeah, by checking here, you're also checking what losses there are due to a coaxial cable. Now, I think it's standard practice in most fabs that if you're calibrating a generator and there is a long cable, you're calibrating the generator to the point at the input of the match, okay? But if you don't do that, or you're in a research lab and you only look at the generator output numbers, don't do that. And so I want to say also, never trust the reflected power number on a generator. So even if your generator says 0, doesn't mean it's 0, okay? I'm a bit biased and going to say always check with a VI probe, but let me give reasonings why this is the case. Generators are typically calibrated with directional coupler technology, okay? Directional couplers, the way they work is they kind of, imagine they kind of take a bit of power off the line, okay? So directional couplers typically absorb some power. I've seen them absorb about 1 watt usually, which may not sound like a lot, but that means even when you're calibrating to 0, well, this thing is absorbing 1. So the 0 on your reflected doesn't actually mean it's 0. It could be like 1 watt. And that can be enough to cause some process instability issues, okay? Like process stability issues. I want to say similarly, never trust 0 watt on the generator output. Like if you turn your generator power down to 0, it doesn't mean it's really 0. It could still be outputting something. Always have an interlock, always switch it off before you do anything, okay? Right. Let's just have a look at a matchbox. So this is the internals of one. This is from a Nordson March unit. So this is kind of older style. But these are variable capacitors. And the way they vary is basically motors twist one of these plates. So then you change the overlapping surface area, which is changing the capacitance, okay? So you have 2 variable capacitors here. You have some fixed capacitors, and you see the inductor in the background. This is a very typical matchbox design. On our website, we actually have a number of blog articles on much more detail on the different types of matchboxes and why one is better over the other, and also how to, let's say, examine them in more detail with a lot of mathematics. So if you go to our website and type match or matchbox, you get lots of articles on these sort of things. So yeah, anyway, they usually contain fixed capacitors, variable capacitors, and an inductor. And the variable capacitors are often called like load and tune, okay? Do note that the matchbox has multiple jobs. So it's not just to match the impedance of the plasma. You also have to strike the plasma. And to strike the plasma, you need to reach what's called the breakdown voltage. So the matchbox also needs to provide initially a high enough voltage to strike the plasma, and then it changes its positions in order to keep power delivery at maximum. Okay, and when power delivery is at maximum, your reflected power is near 0. It's 50 ohms on the 50 ohm side. Okay. So every matchbox has what's called an impedance range, okay, over which it will work. So a matchbox cannot just match to any random number, okay, that you think of on the infinite plane of complex numbers. It will work over some fixed range depending on the choice of capacitors and inductors. Some matchboxes have a very small range where they try to really optimize efficiency to get like 95% of power through or more. Some have very, very broad ranges. They're more useful for more types of plasma, but you don't always get the same power transfer efficiency. So there's a trade-off there, okay? And you must consider if you have an old tool and you're developing a new process, make sure you consider, does the matchbox on the tool, is it suitable for the new plasma impedance you're introducing, or for the new, your wafer, your product wafer that loads into the tool also contributes to the total impedance of the chamber. So are you even suited for that? So do consider this. I've seen people develop new processes and then the matchboxes have to be replaced every 2 weeks because they're just burning them, like, because it's not the right one for the job. So you need to measure what's called the impedance range of the matchbox. And that's what today's live demo is about. Usually the impedance range is mapped out on what's called a Smith chart. So you will only get 50 ohms on the input side of the match if the output side is within the matchbox range. Okay, so there's some finite area where it will work. You need to be in there. Now, again, reality is always a bit messier. Although this is a map of the maximum range of the matchbox, you don't have infinite finesse on the tuning capacitor. So you usually have like step sizes, like using stepper motors. So it's not like this is a fully shaded area. It's really an area with a lot of dots on the inside. So there are little gaps in there. But in general, the range is quite applicable to what's happening, okay? So just be aware of with matchboxes with giant, really wide ranges, you're going to have some gaps in between what it can actually tune to, okay? And just briefly stepping back a bit, what even is a Smith chart? It's a nice visual tool, because impedances can be anything. And how do you represent anything? If you put it on an XY plane, you can be way over there or way over there. This gives you much more finesse. So it kind of zooms into the low impedance regions, so you can see a bit more, and this zooms out on the high impedance region. So you can see a lot on the one chart, and with the appropriate amount of finesse in different parts of the chart. 50 ohms is in the center. So, you want to be right dead in the center of here on the 50 ohm side. If you go here, you're closer to a short. So that means you get like maximum current, basically, but this is effectively a short. Over here is an open. This is where you'll get the maximum voltage and no current. And then you have the inductive side and the capacitive side, okay? So if you're running an ICP coil plasma, you're probably up here when you're in H mode. And when you're running a CCP, you're down here in E mode. In reality, they're always a bit mixed, but typically ICP is up here and a CCP is down here somewhere, typically. And you may notice then there's these kind of circular motions. So as you move the tuning caps and the load caps, you actually move in these little circles. And the matchbox is trying to get to the center region with its algorithms. Right, I'm actually going to skip the next few slides quickly, just so we get a bit closer to the demo. So what we're going to use for the demo are Octiv VI probes. So the ones we're using actually look like this. We're using the ones that have a 12 kilowatt range, but we make ones like up to like big EIA connectors and whatever. We make ones that go up to 90 kilowatts. They're 1% accurate on power, at least up to VSWR of 6:1. We're actually better than that. If you speak to us, we can tell you, if you tell us what impedance you're at, we can tell you what kind of power accuracy you get at that impedance. Different voltage ranges available, different current ranges available. So, pre-match up to 25 amps is good enough, because of that 50-to-1 relationship, you don't get a lot of current pre-match in the 50 ohm region. Post-match, plasma can be super low impedance. It can be like 1 ohm, 2 ohms. So you get really huge currents. So we have high current models available. And then the other thing is these sensors can report typically 10 times a second. And the demo we're going to do today is at 10 times a second. But you can also run a 500 times a second. So if you want to do really, really quick mapping, you could just run your tuners at the maximum speed, running at 500 times a second, and you'll get a very, high detailed map very quickly. But today we'll slow it down a bit. We'll go 10 times a second and slowly do the tune. And the other thing is, with these sensors, we try to make sure that the impedance measurement is as accurate, like is the same accuracy as a vector network analyzer, because typically these Matchbox mappings are done with vector network analyzers, but they only output like 1 watt. So you're not testing your Matchbox at the real powers that it's experiencing. So you don't see the drift from heating or anything like that. Like you're not at the steady heat state that it's typically at. So you don't get the correct map. So these allow you to get the impedance accuracy of an offline VNA, but at the actual powers that you're using with the match. And then the other thing I want to mention is we don't just measure CW. These probes are fully compatible with pulsed RF. So matching with pulsed RF is a whole different story, because you have a plasma that's striking and collapsing possibly thousands of times a second. And a Matchbox has mechanical parts, and it can't move fast enough to match every time. So usually you match to a fixed position where the plasma can strike, and the plasma will be matched to 50 ohms at some point in the plasma on, plasma off stage, or plasma on and decay stage. Somewhere in there, you're matched to 50 ohms, and you choose that carefully. You can use our probes to help do all that sort of stuff. So we'll try to do a demo of that today too. So here you can see like sensor reporting power, voltage, current, the pulse period, pulse frequency, duty cycle. It reports all these things live. So you can also do a sanity check on, is the generator doing what it says it's doing? So before jumping into the demo, what are we actually going to do? So we have a setup that looks like this. Okay. This is how you do Matchbox characterization. Now, again, on our website, there's some blog posts, there's some articles, there's even a video on how to do all this. The purpose of Matchbox characterization. So one is to know actually what your Matchbox range is. So if you're making a new process, and if you can measure the impedance of that process, you know the Matchbox is suitable or not suitable. Okay. Similarly, or like a similar problem, over time Matchboxes wear down. Okay. They go through a lot of heat cycles. They lose the coatings on the inductor coils. The inductor coil gets warped because of heat cycles, things like that. So over time, they need to be refurbished and replaced. So you want to make sure after your refurbishment, what you get back is correct. So this is a way of doing a check before you put it on your tool and put up production again. The idea is, in an ideal world, when something comes in for refurbishment, or even at the refurbishment site, they do the Matchbox map as a quality check. Do we still match to the same positions as we did before the repair? Okay, so it's a quality check. So here is how it's set up. And it's a bit backwards to what you might think. So the generator is actually attached to the Matchbox output. Okay, so where the plasma normally is, we're placing the generator. So we're pushing power backwards through the Matchbox. Okay, and then the inputs on the 50 ohm side, instead of a generator, we have a 50 ohm load. Okay, and that will absorb all the power through this. And we have a power meter, the Octiv on each side. Okay, so what we're going to get from this are two things. So the input meter is going to tell us the impedance range of the match. The output meter will just keep reading 50 ohms because it's on the 50 ohm side. So this first one will give us the impedance range. But because we have the second one, we're actually going to see how much power is making it through the match. So we'll have power at the input, power at the output. So that means we'll also get the efficiency of the Matchbox as a function of position. Okay. And you'll find that in some positions, the Matchbox can be really efficient, like 90–95% of power getting through. I've seen as low as 50% getting through or worse as well. So so we'll get both of these in the same data set. And yeah, we're hoping to get something that looks like this. So yeah, and here's just, by the way, examples of, efficiency versus like phase angle that you measure. And this is a map, instead of on a Smith chart with the circles, this is the real and imaginary plotted. So this is another way of representing the same area of the Matchbox. Okay. So yeah, I think at this point we can get on to the live demo. So what I'm going to do is I have to exit out of this and open up the Octiv software. And I need to disconnect to connect to the sensors. So I'm going to, so I'm upstairs there. This is all in the lab downstairs. So this IP address. And then this IP address. So connected over Ethernet. The sensors are plugged into our network, and I'm on the same network, so I can access the sensors from anywhere in the building, as long as I'm on the same network. Now I'm on Wi-Fi, so hopefully this is fine. So what I'm going to do, Sarah, can you hear me? If you're able to unmute, if you're not, just send a message in the chat. What I'm going to do is I'm going to start a scan. Oh, I want to actually be, let me reconnect to the sensor, sorry. What one dropped? So that was 10.42. This is the benefit of doing this over Wi-Fi. There you go. Perfect. So Sarah, when you're ready, can you move the load and tune? Okay, I'm getting messages in the chat that you guys can't see. So yep. So load and tune, one moves in a large way and one moves in a small way. So there you go. You can see it's starting to move there. So you can see the map being made on the Matchbox. So the 50 ohm sensors in 50 in the center, and then this is the non-50 ohm sensor monitoring the Matchbox impedance. And you can see here the difference of power. It's not very much, so it is an efficient Matchbox. Yeah. So the way we're going to do it is, and the way that's happening now is, we're moving tune from max to min, then we're moving load from max to min, and then we're moving tune backwards, and then load backwards. So that's how we do the full map. So, yeah. Now, I asked my colleagues to do it slowly, pressing the button, but you could just hold it and sweep this out super quick. But I want to get a nice kind of detailed curve map. Okay. This load is done. Fortunately, my colleagues, I think they can't unmute because we're in a webinar, so they can't speak and tell me what they're at. But there's the next part. And then at this point, it probably should sweep around the edge. Yeah, the efficiency is pretty good. You can go a bit faster if you want, guys, because we have to go the whole way around the edge of the chart, so it doesn't matter if we go a bit too fast. Yeah, perfect. Yeah, just hold it down. Because you can either tap the load and tune, or you can just hold it and let it go really quick. So, but yeah, so that's actually a full map. So that's the load max to min, tune max to min, and then reverse, and that's it. So yeah, that's how easy it is to do the map. So we have a very, very broad Matchbox, as you can see. I'll actually stop the scan. So yeah, we have a very broad Matchbox for our research chamber, obviously. And then if you were to do like every possible position, so we did max to min, but if you were to do all possible pairs, what you'd end up with is a series of dots all throughout this region. And at each one of these dots you can match. This data can be exported. So you just go to file and you actually go to data display and export, or you can save. These actually auto save to a folder. But you can export this data, and then you can make those plots that we mentioned before. So you can either plot out the Smith chart or plot the reactance versus the DC resistance, or you can look at the efficiency versus position. But you can see these were like the power loss in the match was minimal. There is a difference between the two curves, but not very much. Yeah, so that's pretty simple. let's move on to pulsed RF. So can you send a message to my team when you have the pulsing is on. So I see 1 kilohertz, 50% duty cycle. I will load up the Smith chart and I'll press start. And then whenever you're ready, if you want to go through the same procedure. So I've kind of skipped the step here. In the Octiv software, let me move this out of the way so you can see it better. In the software, there's time resolved and pulse trend mode. So time resolved gives 1 microsecond resolution on the data. Okay, so you can so there it is. It should make the same map in principle. So you can actually look at how the pulse shape is on a 1 microsecond time scale. Okay, and if you do that with a plasma involved, you'll see that even though you have a square wave on the 50 ohm side, on the non-50 ohm side, you're going to have something more complicated because it takes time for the plasma to strike. It takes time for different species to absorb the power, and then there's also an afterglow stage. And what you can do with the sensor is you can kind of tune at what point you're matched at 50 ohms. Now, in this case, this is all data taken at 100 microseconds into the on time, but you can vary that. Oh, I think my sensor disconnected. Yeah, this is what happens when you're on Wi-Fi. I should have plugged in. This was this one here, 10.42. I think. Oh, I have to click connect. Anyway, so you get the point. So that's how you do the matchbox mapping, and it's pretty straightforward. Okay, so thanks to the team downstairs for doing the motion on the Matchbox. Maybe stick around, so if people have questions later on, we might be able to show some other things. I'll jump back to the presentation. Perfect, I hope that's up again. So a few things to note about the data we just took. So when you do a Matchbox map the way we did it, because we're looking backwards into the Matchbox, we actually have to we actually get the complex conjugate of the Matchbox range. So what that means is you have to flip the results upside down. So the map that we have here, you basically change the sign on the imaginary part of the complex impedance. So if it's positive, it's negative, it's positive, and that will flip it. And then that's the correct map for that Matchbox. And ideally then your plasma impedance, so if you have the ability to measure what the plasma impedance is, that should be within that range. And then you can check, okay, my plasma impedance is this. If I look at my range, I have this efficiency at that point. Okay. And you can plot this, efficiency as a function of the impedance or the load or whatever. Okay, so the last section of this is just what other applications do VI probes have. Let me go through here. Yeah, so I wanted to skip to here. So some other applications, if you're able to install a VI probe, so in the 50 ohm region, you're kind of hidden from the plasma. All you can see is the forward reflected power, if you're at 50 ohms or not. That's pretty much it. The Matchbox acts as a filter for like the plasma harmonics that are generated and so on. So you pretty much completely use visibility to the plasma. So if you can put a VI probe after the Matchbox, that voltage and current and power and impedance data can be used for other things. So one of the other things, if your tool does not have a VDC readout, so if you don't know what the electrode voltage is, you can use a VI probe to get that data. Okay, so here's an example of like the waveform from our VI probe. Blue is the voltage waveform and red is the current waveform. And you can see the current waveform on the plasma side is quite distorted. And the reason why is the plasma is emitting harmonics. So I'm looking at the full waveform with harmonics that are being produced by the plasma. it all comes down to this idea of an equivalent circuit of the plasma. If you do the maths of that, you can see harmonics come out. But anyway, typically, it's kind of a rule of thumb. The peak-to-peak voltage, half of that is going to be your VDC, pretty much. So here's a real example. Like we took Octiv data and Semian data at the same time. So this is a measurement of the ion energy distribution function. The ion energy is in blue. You see most ions here. The average energy is about 1100. The peak-to-peak voltage was 2.2 kilovolt. So it's about half. If you do a bit more analysis of these curves, by the way, you can actually pull out the full IEDF. But in general, half of the peak-to-peak is your average energy. So this gives you information on what your ion energy are impacting the surface. I mentioned earlier that you can do the time resolve mode, so you can actually monitor what the impedance, voltage, current phase is on a microsecond time scale when you're pulsing the plasma. So you can look at plasma evolution. In this paper, they were looking at how different frequencies impact what plasma impedance you get. And it was really quite different for different frequencies. Okay. Also, I should point out here, if you look at the voltage, you can actually see a voltage spike. So you can see the striking. This is something that people want to avoid or control. So you can use our sensor to, like, say, fine tune. Like when you're doing pulsing, you can choose a skew rate, so how quickly the ramp up happens, and you can adjust that to minimize like overshoot during the plasma strike, because this overshoot has a risk of damaging the wafer or causing arcing inside the match. So you want to minimize this, and you can play with the skew rate to fix that. So that's something you can do in real time with the Octiv sensor. You can also do live ion flux monitoring, because you're monitoring the current. The real component of that current, so current it's also a complex number with RF. The real component of that current is essentially DC current, and by, let's say, the law of conservation of charge, what's hitting the wafer surface and what's measured as DC current should have a 1-to-1 ratio. Now, in transmission lines post-match, it's not a linear transmission line. You do have high voltages in some places, so that's not. You need to be as close as possible to the electrode to get this right. But if you do this, you get the real component of the current, which is just the current measured times the cosine of the phase. And you know the area of your electrode, and from that you can get the ion flux. And that ion flux will be linear with deposition rate, as shown from this paper, or linear with etch rate as well. Okay, so we've demonstrated both in the field. You can use it for live monitoring, or at least looking for drift in your etch rates. There are some papers that have actually started correlating the data from our sensors, the external sensors to internal sensors. If anyone's interested in those, you can actually get electron temperature, plasma density. You can get a lot of information like correlated between, the external sensor and internal. Similar to how you can use optical externally to get these numbers, you can also do it from an RF probe. Yeah, and that's pretty much it. So I will now have a look at the questions that have been asked. You can access the Q&A. David Martinet asks, thanks for the webinar. Can you do it with only one power meter? Yes, you can. If you just have the one power meter, put it so you're facing the output of the Matchbox, and that will give you the impedance map. Now what will be missing is the power efficiency, but you could just repeat the test with the one sensor on the opposite side, and then map the two bits of data together. Fred asks, why do you do the measurements with the test RF source on the output? So if you did it the way you'd expect to do it, so if you did, generator 50 ohm side, then output, and then some other load, actually, maybe in intuitive ways, if I go back to this diagram. Where's the diagram? I want to go back to the laser ones. Yeah. So if you're on the input side, you're pretty much only measuring the variance of this part. So what you'll see is you'll see a bit of motion around 50 ohms. Like that's it. You don't actually get what you care about is the sweep on the side of the plasma. Because that's going to be the large range. The sweep on the side of the 50 ohms is usually like, 40 to 60. It's like a smaller range. So it's not, you want to, like, the idea is the Matchbox output number should match the plasma impedance, pretty much, right? If that makes more sense. So you care about what the output impedance is, and you do that by measuring what the impedance is from the point of view of the output. The Octiv sensor is always measuring what the load is after it. So you need to have the output after it. I don't know if this makes sense, but if you try it in the lab, you see pretty quickly that you have to do it this way. Anonymous asks, what are the benefits of doing pulsed RF for processes? Now, that's a big topic. And I actually have a full webinar on that. Actually, 2 webinars on that. So I have a webinar on pulsed RF processes, what it's all about, what's going on. And I have another one which is on challenges of the semiconductor industry. But in short, it's a way of reaching higher energies, because you can have it that, you have much higher instantaneous power, like much higher instantaneous voltage, so you can pull the ions down at higher energies, but the average power is lower. Like you keep the average power down. Like if you think about, trying to reach 7 kV, 8 kV, 9 kV ions for dielectric etch, or especially very high aspect ratio dielectric etch. So you want as high as energy as possible of the ions, so they're mostly straight down. If you want to do that with CW 13.56 megahertz, you probably have to put in 100 kilowatts or some ridiculous power. But with pulsed RF, you can actually, you can have higher instantaneous power. There's other things that happen as well. Like there's a balance between power, current, and voltage. So by kind of reducing the amount of current the plasma produces, you increase the amount of voltage you get. So this is all covered in the seminar, the other webinar. So I can, if you send me an email afterwards, I can send that to you, the slides and the details. Another anonymous person asks, can you do similar measurement with fixed match and frequency agile generator? Yes, actually, that's a good point. So there's actually multiple ways of matching. The matchbox that you see in this picture is I'm going to call a classical match. There's actually also they're called solid state matchboxes, which are basically just, instead of having a tuning capacitor that slowly moves, you just have lots and lots and lots of capacitors and a very fast moving switch that can just switch between them very, very quickly, like electronically. And that can let you do very rapid matching. Well, another way of rapid matching is, instead of changing tuning positions, change the frequency. So I showed data in this that, impedance and everything is totally different at different frequencies. Where is that graph? This one here. So same chamber, different frequencies, totally different impedances. So you can move the frequency a little bit. It's called frequency tuning. Our sensors are frequency agile. So whatever we were measuring today at 13.56, but the sensor will do plus or minus 10% around that, and it will track the frequency. So yes, you can do this experiment also with frequency tuning. Yeah. Jothy asks how to troubleshoot using VI Pro for individual location of wafer issue like RF coupling. That's a bit trickier. If you have wafer coupling issues, usually you see that as reflected power, but not always. Like the matchbox might be able to match to the incorrect capacitance from the wafer not sitting correctly. Okay. If you're after the matchbox, you can actually very easily see issues to do with things like coupling to the wafer. The reason why, well, there's a few reasons why, but the main reason is a wafer not coupling correctly is often to do with it not sitting flat or not sitting correctly. And if it's not sitting correctly, you get a different capacitance. So you have different sheet shapes, you have different gaps forming, so you get different capacitance. So that's different chamber impedance and different harmonic output. We've actually implemented alarms in the field that run on high volume production purely for wafer coupling due to wafer misplacement. And it's very easy to detect because you have such a massive change in the RF line characteristics with a change in wafer position. Like you can even actually with the RF tell the difference between one product and another because they have different capacitances that you can tell the difference between different products. Another attendee asks, if you have a bad match, How can you use this measurement to determine what adjustments to the tuner are required? Great question. Can you send me an email afterwards? So one of the blogs on our webpage talks about how you change, like I mentioned a Matchbox as a fixed capacitor. So a fixed capacitor is actually a way of moving the map. So one of our blogs, I think, has the mathematics behind how you calculate what fixed capacitor you'll need to move the map so that you're in a better range. Okay, so send me an email. I'll send you that blog post. Hugh asks, would you go over again how to measure the efficiency of the RF match? Thanks. Yeah, sure. So basically, as you saw, when we have the input and output sensor, both are measuring power. Okay, so you literally have power in and power out, and it's just a matter of plotting those versus impedance. Now, plotting that versus complex impedance might be a bit tricky. So you could plot versus phase or, a single parameter. But it's simply that, like, at what positions do you have, it's just, you do is like power out minus power in over power in, I think is the equation. So Hugh, I will, I know your email. I actually have a document which has the equations to do all these calculations. I'll send that to you. It's also on our website. Jyoti asks, Match is already taking care to minimize the reflected power. So how does the VI probe tell the RF power delivered across all zones of the wafer? Okay, so two things. The Matchbox is trying to minimize reflected power, but it doesn't always succeed. And there's two reasons. Like, it tries to use an algorithm to, to optimize the tuning position, but that doesn't always reach zero reflected. And then there's also the thing that on the generator, zero doesn't always mean zero. We've had clients where, like, they were having yield issues, like noticeable yield issues. And when we went with them with a VI probe, the first thing they noticed was that when their generator said zero and their match thought it was matched, it wasn't really. And when they manually tuned the match to actually get to 0.0 reflected, the chamber processing issues they had went away. Yeah, so don't trust that it's working correctly, I would say. Regarding power delivered to all zones of the wafer, you're talking about uniformity there, yeah? Basically, right? Because you want to have the same power at all points. That is trickier to do. Is it possible to monitor the uniformity with a VA probe? Yes, for certain chambers. If you have a chamber which is 300 millimeters, okay, and you're using a frequency that's 13 megahertz or above as a powered frequency, you're going to produce higher level harmonics, right? So if you power plasma with 13, you're going to get 27 and 40.68 and other multiples. And those multiples all have smaller and smaller wavelengths. And you have to think about quarter wavelength, and you have to think about quarter wavelength considering the refractive index of a plasma. So it might be even shorter than you think. It's not, refractive index of a plasma is not 1. Okay, it's actually higher than 1. So eventually what happens is you get standing waves forming in the plasma because of these higher frequencies being produced, and they cause non-uniformities on the edge. There are other sources of non-uniformities as well, but this is a common one in 300 millimeter tools. Some tool makers build in this kind of, I want to call it like a bleeding capacitor in their Matchbox that kind of suppresses all the harmonics, and that really helps uniformity. And you could use a VI probe to make sure that those harmonics are low. So if the harmonics are high, you're going to have more non-uniformity. When the higher harmonics are low, you have better uniformity. So that's one way of monitoring that. Fred asks, can you comment if Matchbox characterization is currently in use for better tool matching? Yes. So actually, I can't mention names, but we have clients who design Matchboxes, and they would design them for a tool, and they would do this map. Like, the people who actually design Matchboxes are good enough that they can model them, right? So they'll have a model that predicts things, but they have to measure what it is in reality, because you have mechanical imperfections and other things, right? When you actually manufacture these things, invisible problems. So they use our VI probe to check the map, make sure it matches what the theory is, and they use the VI probe to check the plasma impedance, and then they go and adjust, put in a different fixed capacitor to move the map to match the tuning impedance. So we do have clients who actively do this process. And we also have fabs, which use our VA probes that when our sensors come in, or when a refurbished Matchbox comes in, they do the quality check before putting it in back into production. Also, some Matchbox refurbishment places use our probes for that purpose. VI probe is telling the global, not the individual point. That is true. It is telling the global point, but there's a lot of extra information in those harmonics, and that can correlate to things happening, at least a global problem it can identify. But you're right, monitoring individual points of the VI probe is not really possible. Yeah. For Jyoti, there's a nice paper that shows using a VA probe to look at uniformity. I can share that with you afterwards. In the case of 2 RF generators connected to the chamber, is there any way for one matchbox, say bias match, to talk to the other matchbox to shorten the impedance match time? Well, yes. So like you have sensors. So if you had a VA probe on the output, okay, so we've just made a map of a matchbox. So that means we know for each load and tune position, like we didn't actually note the load and tune here, but for matchboxes that you can control like remote, like digitally, you could pull data from our sense with the API and pull data from the matchbox, and then actually make a table of tuning position versus impedance. Okay. So then you could say plasma strikes, VA probe tells you plasma impedance is this. That means this number on the table, go match that quickly. So you could use this to speed up the matching. But you have to integrate the sensor and have everything communicating. But that's a, fairly straightforward task. Yeah. David asks, has another question. How to reduce the power consumed by the matchbox, changing inductance. That's harder for me to answer. Yeah, that's harder for me to answer. Most of the power loss is in the inductor, to be honest. Most of the power loss is there. Like making sure you have a really good quality code. Like if you remember, RF travels on the outside surfaces, the skin depth, right? So what really matters with an inductor are two things. So the thickness, okay, the geometry of it determines the inductance. And then you have to consider, by the way, that when it heats up, metal expands, so your inductance changes as it heats up. So that's one problem. So that's why Matchbox cooling is important, right? The thickness of it is for heat dissipation as well, right? And then you want to make sure you have like a proper silver coating on the outside. And you'll find old, badly behaving matchboxes also often have that, because of heat cycles, that outside coating has become degraded. So inductor is probably the first place I'd look at to reduce the power consumed by a matchbox. You were mentioning, another attendee asks, you were mentioning old RF cables. What do you mean? How do you recognize them? Yeah, so this was actually problems we ran into when we were integrating sensors in the field. So when we're integrating in tools with cables after the match, what we were finding was if we took an old cable and modified it to put the Octiv in and then installed it, sometimes then the tool would not be passing quals. The reason why was because the cables were old. Every time we used a brand new cable, everything was totally fine. But if we used a cable that was 5-6 months old, you'd see an issue. One of the ways we spot issues with the cables in that case, though, is the Octiv sensor also has temperature sensors on board, because we do a temperature correction, like the sensor compensates for how hot it is for its output readings. But we could collect that data, and we could see on some tools running the same process, during the process the cable reaches 40 degrees Celsius, and then after process it comes down again. But on some tools you see during the same process it's reaching 60 degrees Celsius and then coming down. So that's one hint, like the cable getting hotter, that it's no longer as efficient as it was and it needs to be replaced. So checking the heat of the cables is one way. There's probably a way of checking, definitely using a VNA, maybe using a VI probe. We'll have to think about it. Like looking at the efficiency across a cable maybe is one way of checking. So if you had a cable of this length, brand new versus old, maybe you'd see a difference in the power transfer. But heat in real production processes is one way of checking that. How to find or measure the unknown impedance of a plasma. Well, stick in a VA probe if you can. If you can't, if you're able to put in a Langmuir probe, you can actually use the electron density and electron temperature data to predict what the impedance is. There's some models for that are pretty good. Otherwise, it's a bit of mathematics. Like you'd have to do, like if you don't know any of that and you only know power, then you need to know the chamber geometry. You'll need to do like a Lieberman global model to get estimates of the density and the temperature, electron temperature, and then from there you get the plasma impedance. And keep in mind though, it's not just plasma impedance. There's also chamber impedance. Like it's a combination of the two. So ideally, you want to have a VA probe to do that. Please share the presentation or link to all users. Yeah, so after this talk, we will send this out to all registrants. That is the last of the questions. I'll wait a moment if anyone else wants to type a question. But if not, we'll end the webinar and send out information afterwards. One more question. At what intervals do you recommend using a VA probe in a production fab? Good question. If you're in a production fab, I recommend at least using it as often as you do your maintenance cycles, or maybe at some multiple of the maintenance cycle frequency. So you can use it to just check, is the generator outputting, so is the forward and reflected power in the generator match what the VA probe is, like as a sanity check. So that's an independent verification. You can do that anytime, especially if you're seeing problems. Also checking, is my matchbox reaching 50 ohms or not? So if you find that one tool doesn't have as good as yield as another tool, that's probably an early place to check. Is the RF power consumption, delivery happening the way it should? Ideal scenario is that you have a VA probe after the matchbox 24/7, because you get all the benefits of process repeatability and, knowing is the plasma in spec or not, is the chamber still in spec or not? Like you can use VA probes to give yourself full visibility, but I know it's not so easy to just install them in the fab. I get that. But for people who have installed them, they're the kind of benefits they get. Like it's just, you're no longer relying on, okay, 5,000 hours have passed, I need to change all the parts. It actually becomes like, I know I'm in spec, I can keep running. I know I'm drifting, I need to do my maintenance now. So, yeah. Okay, so let's leave it there. And thanks everybody for attending. Send an email to like info@impedans.com or support@impedans.com if you have any questions, or thomas.gilmore@impedans.com, and we'll answer any other questions that come out and we'll send these out to people. So yeah, thanks very much.